And I'll start sharing. Right, so yeah, these are all part of the notes. Well, it's a lot of notes, but these are main note, and there's a lot of side notes for this particular chapter. So yeah, I have to show you guys afterwards. I think this question is taken from the Literature Technology 2 textbook. Not sure, things number 4 or something. And it's a very common, you'll get a lot of problems similar to this, and you'll see once it all integrates. So, okay, cool. Let's just begin. So in keeping with the three-phase and star and delta, what typically happens is, or a situation you're going to get is where we have a load, or one of the loads with multiple loads, and it's going to change configuration. And what I mean by that, it could be supplied at a different voltage, at a different frequency, and maybe with it changing from star to delta or delta to star. And this, in example, essentially encapsulates what I'm trying to explain here. Okay, so what we have is an electrical load in a factory, and it absorbs 75 kilowatts at a power factor of 0.8 lagging as a balance load. And when it's connected in delta to a 415 volt 50 hertz three-phase system, okay. So the term for this load, and this is a typical flow of it, its resistance and reactance to each phase, which will be the same for all. It's a balanced load. And then the power absorbed when this load is connected in star now to a 60 hertz 380 volt three-phase system. Cool. There's actually also your first problem in your exercise pack of the 5 problems which you have to do. So anyway, let's start it. So first things first, right? We need to get the resistance and the reactance. Okay, so we have the power, which is 75 kilowatts. We have the voltage applied, which is 415, and the supply frequency is at 50 hertz. Okay, and your power factor, PF, is at 0.8 lagging. Okay, so they want the resistance and the reactance. So the first thing what you want to do is say P in root 3 VL IL cos of phi. We find the line current, and then we have to then find per phase what the impedance is. So obviously, so we're going to go from here to here. Okay, cool. So we have 75 kilowatts, root 3 times 415 times I line times 0.8. So what is my line current? Can someone get that for me? And all the answers is given there, which is quite nice. And of course, make sure your line current has the respective angle attached to it. Let's see. Can someone give me my line current? Well, it's actually there, but I mean, let's get it. Fantastic. There we go. So it's 130.426. Okay. So we call it 426, 130.42. We'll just call it 43, right? Yeah, 130.43. At the cos of that angle, which is 36.87. You should kind of know that by heart now. Because we connected in delta, we know that the line current and phase current is not the same, and it should be divided by √3. So it's or times 1/√3. Either or. So we can multiply by √3 or just divide. And that's 130.43. And you should get 75.304. Right? At the same power factor. Okay. Now once we have that, we can find the characteristics of the load, being the resistance and the reactance. And can someone please tell me what is my V phase and why? You can unmute your mic and tell me. Mr. Low or Mr. Breed or Mr. Msongo. Muda, Mungo, yep.
V phase is 415, so
4 and 5.
it's the same on delta.
Yep.
Yes, it's the same
Exactly.
on delta, it doesn't change.
Yeah, because your V line is equal to your V phase. So therefore, you're going to have 415 at 0 degrees. And you'll see how it all comes together. This is like a slight revision. It's still it's 3 phase. You're just extending it. But anyway, some guys know this already. So that's minus 36.8, and then times by Z phase. Obviously, you want to do this in a calculator. In a calculator, will return the answer in rectangular form, right? So I'll just leave it open for you guys. So you guys can just quickly do it, and let's see what answer you get. Cool. Now we do one more, then I'll just direct you to what you should practice, at least till next time. So what is the impedance? PJ, you get the answer? Cool. See, Mr. Lowe's got it, and you should get 4.408, and also no, that's right. You should get 3.3067. Okay. Oh, sorry, 483.3066. Cool. 3.3066 and ohms. So I like to just say here. So this is a plus. It'll tell you it's an inductor. And if it was negative, it would have been a capacitor. So I'm obviously repeating this for obvious reasons. So it's very, very important. Okay. So at number 2, right? So we've got number 1, and number 2 states, what is the power absorbed when this load is connected in star to a 60 hertz and 380 volt system? Now, what is important here, guys? Before I proceed with this question, so star, obviously that changes our values. 60 hertz, and 380. What's one of the main things what should happen now once we change our load? Let's say it's a motor into this new arrangements. Super important. Maybe Mr. Mongo will tell me, or let's see.
You're supposed to calculate the new inductance.
Nice, Prof. Sima. Okay. Oh, sorry guys. Sorry about that. I said that's correct, Prof. Sima. What changes is your inductance. And okay, cool. Yeah. So what I wanted to explain was that your impedance, as you've seen here, has two counterparts, right? R, which is the real part, which is the resistance, plus X. And X is deemed your reactance, but your reactance is essentially a frequency dependent resistor, right? I'll just write it here. Why is my anything funny? So if you remember the equations again, because you did an inductor 2 pi f L, right? This is going to be at 50. This is at 50 hertz. So the first thing we have to do is find the actual inductance value and then recalculate our new reactance at 60 hertz. So let's quickly do that. We obviously found our reactance to be 3.3066 equals 2 pi, and this is at 50 hertz. Let me get my inductor value. All right. Can someone just get my inductor value? Once you have inductor value, we have to now change that. We have to find our inductive reactance at 60 hertz. So I'm just going to put it here at 60. So let's get an inductor value. Mr. Bolo, are you following? Mr. Low, Ms. Duba, Mr. Peters? Yes, so say 10.527. I'm quite happy with that. Millihenry. Right? 10.527, 527 millihenry. Then we populate this back into here at 60 hertz. Milli. And we're going to get our new inductive reactance at 60 hertz. So I'm not sure what that value is. Maybe someone's worked it out already. Cool. Fantastic. Mr. Mini, are you following? Mudanalo, are you following? It's been a rough week so far. So let me get my new inductive reactance. Well, guys, so it's a continuation of last semester, but you'll see when it gets a bit more complicated. So you get 3,973. That's correct. Cool. So once we have that, we have a new impedance. So our new impedance at 60 hertz will be 4,48. So this, your resistance remains the same because this is not a frequency dependent resistor. And we have 3,973 ohms. Cool. All right. Let me just quickly see. 9644. Is it 96? What is it? 973, or let me just work it out myself here. 2 pi times 60 times 10.527. I'm just depending on the value. I get 2 pi times 3,97. Yeah, 3,9. I get 966. Yeah, 966. I'm happy with. Okay, cool. Okay, so we again find the power absorber, right? So it's the same thing, but now we need to find the current, right? And this reverts back to V phase equals I phase this. However, we connected in star. Our voltage this time around was 380 volts. Our frequency was at 60. We sorted that out and we install, right? So first thing is first, because we install, we have to divide 380. Our V phase is going to be 380 divided by √3. Cool. And we get 219.393 volts. And that's at 0 degrees. Okay. And then we need to find our current, and obviously our new Z phase, which we have to put in our Z at 60 hertz, which is in a new location, is at 4.408 plus J 3,966. And let me get a new phase current. And as you can see, we have a different current, probably with a different angle as well. Let's get that. All right. So what do we get for our new phase current? I think that's correct. I'm not sure. Yeah, I'm typically going to have the current in polar form. I'll just confirm. Let's see what I get. 219.393. 3.966i. Yeah, 36.99 I get 37, yeah, at 41.98. Okay. So you should get 37 degrees. That's fine at minus 41.978. And we connected in star, this equals line. So now you find our power. It's going to be √3 times our line voltage, which still stays the same. No, sorry, it doesn't stay the same, sorry. Our phase current, which stays the same, which is 37, times cos of our power factor, which is that guy, 41.978 degrees. Okay. Let's get that. And that'll be a power in calculation. Let's just quickly see. So after this, we can do multiple loads now. Yeah, that's the next step. Get power. Yep, 18.095. Fantastic. How did you guys find that? Welcome to S4. Any questions before we move on? It's going to get fun now. Yeah, we call it the last example for the day, and then we'll continue next week. Any questions? Mr. Mungo says good. Anyone else? Ms. Duba, are you fine? Mudanalo, are you okay? James, Simpiwe, are you following? Good, fantastic. Always happy if you're happy. Dr. Duba. Mr. Briat, are you good? Okay. Right. So you do the next one. So now we're getting there. So I'm going to do this one, and then I'll show you what you need to get going, and then you do power factor correction, and you're basically done. So I'll open a new whiteboard here. Okay. Let me just see here. Okay, Mr. Ashipala, thank you. Fantastic. Okay, so here it gets fun. This is in the reads book. I will post that relevant chapter later on. So what do we have here? Right, so I'll sketch it out so long, and you'll see how it all comes together nicely. So we have two alternators. Someone saying something? Okay, thank you, Mr. All right, I'll just call it generator 1, generator 2. And they are powering a few loads. And they typically supply that parallel. If you do see a question where you're supplying multiple loads, it's always going to be in parallel. It's never going to be in series. I'm just making you aware. So we're powering one load. Right? Maybe I can just make a box for it. The first load has 40 kilowatts at a unity power factor. A power factor of 1. We've got a second load. Right? Obviously, no transformers here, just assuming it's directly coupled like this. Second one is at 40 kilowatts. I'll give you a moment to jot this down. Your power factor is at 0.85 lagging. Your third one is going to be 30 kilowatts at a lagging power factor. So it's 30 kilowatts at a lagging power factor of 0.8. Super important. 8 lag, because you can have a leading one, and then you have a last one is at 80 kilowatts. Cool. 4, and this is 80 kilowatts. I'll give you a moment to jot the question so you can have it as well. Power factor of 0.7 lagging. Not so lekker. Okay. Let me just make sure this is right. And then they say the armature current of the one machine or alternator is 100 amps. So we can say for the one, and on this bus, it's producing 6,600 volts. Sorry, 660 volts. Believe me. And I1 is at 100 amps at a power factor of 0.9. Okay. So you've got two generators powering multiple loads. It's becoming more real life type, you know. And what they actually want, they want to know what is the power output and power factor of this machine. All right. So I'll give you a moment to read the question, write down what I've written down, and just see if you agree with me. We'll go over it together. But the idea is that we have two synchronous alternators in parallel powering those four loads there, right? They're generating a voltage of 660 volts, and obviously they give us the individual loads. The loads could be air compressor, motors for the air compressors, any electrical, the transformer, it could be any electrical equipment. Typically use a power factor of 1. That's purely resistive load, so this could just be lighting, for instance. Yeah, so they give you different types, and they're all at different power factors. This is what I mean by multiple loads. And the objective of this case, this time around, is to find the load of this particular generator. Okay, so yeah, so read the question, and I'll give you guys around 3 minutes to we'll just read the question and jot it down. It's the last one for the day anyway, so we should be done at 4. Anyway, okay, so I'll give you a few minutes and then we can proceed. And let me know if I missed anything in terms of the, you know, the one of the values or something. Oh yeah, by the way, this is at seconds level. I'll tell you when we at chiefs level. So we're getting there now. Seconds, this is second/chief level. Yeah. For 3-phase balance load. This is what it's all about essentially. So now we're combining a lot of things. Another thing I've missed, sorry, is that it's connected in star, which is important for whatever reason. And fortunately for us, they didn't tell us how the loads are connected yet. So that's perfectly fine. So we're assuming just as is. We don't actually need that, but okay. So read the question and then just get all the particulars down. 1:15, I will proceed and ask you guys questions. Check. Mr. Peters, you get the question? Mr. Mart, do you understand the question? Mr. Veerling, Mr. Mongo, Ms. Duba, Murad, you guys understand the question? Nosipo, Mr. Duplessis, Mr. Msongo. Fantastic. That's super important. As long as you understand what the question is asking. Does the sketch help? Okay, cool. Yeah, that's the idea. That's why I was talking about those sketches in the first, the introductory kind of thing, just to have some kind of illustration of what's expected. But this is where we need to be roughly. Okay, cool. So let's see. Just give you some more minutes. You guys need some more time to write. Are you guys done? Just say done on the chat if you're done, so I can start. I'll give you like 2 or 3 minutes. If James is done, then we're done, eh? Let's see. Muda, are you done? Okay, done. Fantastic. So let me proceed. I've got enough dones there. So what we have to do now, I can show you. Okay, cool. So what we do is we need to now, there's many ways to obviously do this in terms of the total load. I'm just making you aware. But we need to find the total power and I'll show you now. Let me just write it out for you. So I'm going to say, can I say SG plus SG1, SG2 will equal all of this? Does it make sense to everyone? Oh, sorry, SG2. We can get all this in a pattern power. And what we're going to do, once we have this one, we have that one, we have that one, and we have that one, we can subtract SG1, because we can obviously find that using our formula, √3 VR I line, and we can get SG2. Is everyone content with understanding of what we're gonna try to do? But obviously, I'll try to break it down further. So I recommend sketching a table, especially when you have multiple loads. Okay, so we have 4 loads here, right? So I'll just see if I can manage. So I'm gonna call this load P, Q, and then S. I think that's okay. So 1, 2, 3, 4. So let's get the loads first, right? So we'll come back to the generator now. But let's get it. How much kVA in power is all these loads drawing on that line? All right. Forgive me for my skew lines here. Could have spent more time making it neat. Okay. So first thing is first. Our first power is 40. There's no reactive power because there's no power factor. Is everyone happy with that? Can I give it a tick? And to write this in complex form, 40 plus J0. And I should have mentioned that S is also S plus. I didn't actually mention that on the slides. Are we all familiar with that first of all? Does anyone have a debate with that first? Realizing now, I didn't actually talk about that. This is the same as this. Remember, it's the resultant of the two. But that's alternative convenient complex form to put it in. I should have actually mentioned that there. Is everyone happy with the first load? Complex. I should actually write it, put it in somewhere. Cool. So let's do the. Can you guys quickly do the second one so I can just verify that? To find the power, reactive power, and then put it into your apparent complex form there. Okay. What did you guys get? Try to populate all of them. I'm sure you guys can figure that out. Mr. Mungo, have you got the first one? So obviously, you know, a power factor is a ratio of a true power to apparent power. That's the first one. And we're gonna get so this is 0.85. That's P, which is 40, sorry, over S. You're able to get that. So we already know this is 40. What is this? 40 divided by 0.85. That's 40. Okay, let's get Q rather. I think it is. Yeah, 47.05. I wanted a more. I want P and Q on its own. So let's just rather do this. So for the first load, so sorry, load number 2, let's get an angle. Obviously there might be more convenient ways to do this, but I'm just obviously just making it more detailed for, especially since it's the first example. 788. We have P over here, so let's just get Q, which is over there. So Q would obviously be sorry, sine 31.788 is opposite over, sorry, that's tan rather. What am I saying? Yeah, tan 31.788 will give us Q divided by 40. And we can just put it in complex power form there. Everyone content with this? What is Q? You guys can obviously populate the rest, which I'll verify afterwards. Does anyone understand how to get Q? Does it make sense? We're using P, Q, and then S. Because it's lagging, we can make it, we'll make it negative, right? Sometimes you make it positive, but yeah, lagging, well, it's negative 24.789. This is up for debate, depending on how you want to call it, lagging or leading, but yeah, we'll make it negative. So 27.7895. Okay, just bear with me there. Then in that formula, 40 minus J 27.7895. I just need to remove this here. It's 27. Is it 24, 27? Ah, it's 24. That's Q2. You can see it's not difficult in terms of maths, but it requires a bit of work. 24.785, 7895. Cool. It all makes sense in the end. Okay, so do load number 3 and load number 4 as well. So obviously this is going to be 30, that's going to be 80, and then you're going to need this all remain negative. Cool. And you need to get the parent powers here. Okay. Let me know when you got the rest there. I'll wait on you. Is it negative 24? I don't agree with negative 24 point what. I'm waiting for load 3's reactive power and load 4. So what's my Q3 and Q4, please? 22.5. I concur with that. Yep. Thank you, Mr. Silver. Professor De Silva. Let's get Q for that. And also in this form, there's many ways to kill this cat here, but I'm just, yeah, we'll see. Okay. I thought this example would take time. And Q4. And these questions easily go from 25 to 30 marks, depending on what's happening. But typically 20 odd marks. 81.616. I'm happy with that. It's a bit off from what I've seen. 81.662. Okay. Then I just corroborate that particular value. So you get a mark for each of these here. Well, you might get a half a mark for those there. You guys agree with Q3's value? Okay, Mr. Ashipala agrees. Mr. Sima, is everyone following? Any questions before we move on? Mr. Duplessis? Mr. Yengwa, so is P not 36? As I said, it's 30, man, not 36. Excuse my handwriting. I just said write down the question. That's 30. Is that sorted? Let me know when you're done. So all of this is load, S loads. I'm going to call it SL. So let's find the total of SL. Obviously, you have to use your calculator here. And just get the total of the loads for me, please. Can we all get that? Mr. Silver, sorry, Professor De Silva, can we get the total of the loads? Is there any questions? Guys, please, he's done already. That's 190. The chat can add all of them up, so that's 190. And can I have it in polar form? That's what I actually want it as. I don't want it in rectangular form. So 190 minus 128,906. J. And in polar form, what would it look like? What would it be? 2 to 609, sorry, 2 to 9.601 minus 34.155. And our unit is volt. Is it kilovolts? No, it's all kilowatt ampere. It's all kilovolt. Kilovolt amp. You guys follow so far? Super important. This is my favorite section in electrodes. This is synchronous machines, yeah. I enjoy teaching this one. Simple enough but long, yeah. It's simple. Does everyone concur with the total loads? Dus de precies is yes. Mudonalo, Dosipo. Mr. Monmu says yes. Okay, that's enough. Fantastic. So what happens now? Reverting back to where we were before, it's SG1 plus SG2 equals the S total loads. We need to get SG1. And SG1, just quickly get it there on the side over here. We need to find the pattern power, right? So it's root 3 times the line voltage of 660 times 100. And they really give us the angle there, the 0.9. So it'll be root 3 times 660 times 100. And that's 114.315. And at an angle of, it's lagging, right? So it's cos of 0.9 minus 25.842. You guys agree with that answer? This is S1, SG1. Yes, Mr. Silver's on fire here. It's good to see you on fire. That's SG1. Does everyone know how we got that? I'll give you a minute to absorb that. And obviously, if you're sharp enough, you can find the power produced by that generator. You guys, 2 minutes, and then yeah, get S load. Sorry, SG2. Okay, give it 25 to I'll start. I'll give you guys a moment. Did you guys get the answer? Let me know what the answer. So they want the, let me just be clear. They want the power factor and the active power. So they want the true power. So they're saying the power output, P, and the power factor. Yeah. So yeah, work it out. Anyone got the answer? Mr. Silver, you know us to share your answer. Mr. Sima, Mudanalo, Mr. Ball, Mr. Ashipala, Mr. Monmo, what's your answer? I'm looking for the final answer there. So SG, I think we just do it here. SG1, oops, plus SG2 equals SL, which is 114.315 at minus 25.842 plus SG2. And what is SL? SL is 229. 0.6601 minus 34.115. Therefore, SG2 will be what is it? 117.66 at minus 42.23 degrees. And obviously, if you put this into from polar form, you can just do it in a calculator. 177.66. Just type it in your calculator or give it in rectangular form. P will be 131.55 and Q will be minus 119.41. What's this? Volt amps. Oh, sorry, my bad. I put 177. Forgive me. Minus 117.66. Yeah, 87.12. And minus 79.08. Cool. That's the power. Oh, amen. Okay, they wanted the power, and I said the power factor. Let me just check if the answer is correct. Yep, power factors should be attached to that. And the power factor, so this is the power, 87.121 kilowatts. And the power factor is cos of 42.23. Welcome to S4. .4045 lagging. Okay, How do you guys find that? Amazing, good. How do you guys find that? I like to use a triangle when I get stuck. No, it's fine. No problems. That's perfect. But this is a good question. Very good question. And obviously now we can find the total will be the same there. Yeah. An add-on would be like, how do you increase the power factor, for instance? Is there any questions before I conclude the lecture on this particular problem? Not difficult. Okay, your total, no problem. 40, 40, 80, 80, 160, 190. Yeah, okay. So mark allocation for a question like this, I'll probably give like 1 mark there, 1 mark there, 1 mark there, 1 mark there, 1 mark there. 1 mark for the load, like, oh yeah, this could be 1 or 2 marks depending. SG2, this is definitely 2 marks, obviously. This would be, oh, then what's required is typically 1, 1, 1. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Around 13 marks for this. Oh, and maybe this is 14, 115. Then probably you'd have like power correction. I'm just giving a straight mark here. This could be half marks and stuff. So around 15 marks for this one. Without the power, improve power factor. Yeah, we'll get to that. That's in the next section. I don't want to overwhelm. So is there any questions or this question before I move on? Okay, cool. So let me just stop sharing here. Get back to the slides. And then we can conclude. Okay, so I've just pasted this here. Just to, I didn't actually have it in the slides and I kind of overlooked that. This was a single phase multiple load example. You can try that one out. This one I recommend trying as well. Very good one. This is the one we did, and that's the one we did. So I'll post this part of the textbook with this particular parts for you. I just need to collate them properly. And then next week we'll start on power factor correction. So I think half the lecture will spend on 3-phase. That's where we're going to get to that. And then, like I said, let's see the type of examples I was referring to, where you can see I have 1 load, another load, another load, another load. We have 5 loads here on the phase currents, and then on the total input current. You know, this is a nice question. And then I take motor C. I say motor C is now used in a different location and different frequency. So you see that's around 26 marks. There's another nice example like which we did for practice. And I remember this was in test 1, also from another textbook. So there's a few examples to do. Plus, let me open the actual main note. So there's a lot of notes, and try to do all the examples in all the individual sections that I'll give. I just want to open another one quickly. Let's type just a main note. So there's a lot to practice for this thing. Yeah, one day I will write my own textbook on this. Yeah, given that I have enough time, especially to technology 3. I'm just give me one quick moment. Notepad. Why can't I see 3-phase synchronous? Note back. Why is it not here? Oh, good, cool. Just 1 second. I've cut out certain chapters and stuff. For your okay, cool. Just gonna share it quickly. Yeah. Just rotate it before I share. You guys can have a look at it. So yeah, so those examples on the slides, but start off with these ones. So these ones is the first problem we do. This is like, it's very old. It's in English and Afrikaans on the next page. Try those ones. There's another nice one, and also there's also a Word document which is tutorial. Try those, but look at the slides and look at this note here. And yeah, and I will be posting something extra, but obviously I'll make an announcement for it. Okay. Is there any other questions, guys, before we conclude? And let me go to this. Repost the slides now quickly. Any questions, guys? Can we conclude? How do you find today's lecture? Okay. It's the end of the day. Okay, guys. Ending session.